Hello, Teledyne Labs would like to welcome you to today's webinar, What Can We Learn from Scouting Runs? Today we are joined by Jack Silver, who is one of our application chemists. Before we begin, I would like to share a few items. If you happen to run into any issues during the presentation, such as with audio or visual, please leave the webinar and return. This oftentimes will clear up those issues. This webinar is being recorded. Therefore, we will be making it available to you in the near future on our YouTube channel. If you have any questions during the webinar, please utilize the questions functions within GoToWebinar, and Jack will answer at the end. So with that, I would like to welcome Jack.
Hello, and thank you for your time today. Although this discussion uses Teledyne Labs products, the discussion is general enough to be helpful with any purification system. We will discuss several things today. The most important questions are what are a scouting gradient, and then why do we use them? In addition to verifying reaction outcomes, scouting gradients are commonly used for method development, and we will discuss various techniques using both analytical and preparative instruments. Assay-directed method development is useful for natural products. Scouting runs also allow for detection optimization. They can suggest loading capacity, how to dissolve the sample for the big column, and also how to see the best column and solvent system to use. I'm also going to discuss a couple of terms here. I'll use the term B solvent, the strong solvent, which makes the compound elute through the column, while the A solvent or the weak solvent modulates the strength of the strong solvent or the B solvent. I'll use this term B solvent for supercritical fluid chromatography, SFC, because it behaves like normal phase chromatography. A solvent modifier is something added to the solvent system that is generally used to change the solvent pH or solvent selectivity. So a scouting gradient is fast, and it covers the entire solvent range the column or instrument is capable of running. As a standard method commonly used with a mass spectrometer, it determines if a reaction has occurred and helps to find the correct peak for purification within the gradient method. Several scouting runs are commonly used to determine if a solvent modifier is needed, high pH, neutral, or low pH, and scouting gradients are used to screen columns and solvent to maximize resolution and, of course, for method development. When I say that the column will be run over the entire solvent range of the column or instrument, some columns may have solvent composition limits, such as some chiral columns that degrade with certain solvents, and SFC systems are typically limited to 50 to 70% strong solvent. Scouting runs allow development of methods that purify compounds quickly to save time, money, and solvent. The most common workflow used today is depicted as the conventional workflow on this slide, and is described in the reference on this slide. The focus gradient workflow decreases the number of steps. The gradient or isocratic method is calculated using peak track software on the preparative system. While this isn't exactly a scouting gradient, this example shows some of the data from a scouting run. The mass spectrometer allowed positive determination of the benzidine peak that eluted a bit later. Scouting gradients have long been used for method development, and we will discuss 3 different methods to create gradients from scouting run. One of them is the iterative method development, which people new to chromatography will often try. We will discuss zones, and we will discuss the time on target and related algorithms. For the purposes of this slide, let's assume 20 by 150 millimeter HPLC columns for the time and solvent estimates. An iterative method means that you make a guess from the scouting run, do a run and improve the guess, and then repeat until the retention is good enough. In this example, at least half a liter of solvent and 17 minutes is needed for each attempt, and unless you're using a fraction collector, it uses solvent sample on each try also. None of these peaks need 100% B solvent to elute from the column in a timely fashion, and users often make their initial guess based on the draw volume or gradient delay represented by the green gradient line. This causes earlier elution, but it's still a useful starting point. Many chemists have a chart like this near their preparative LC system. It shows the analytical scouting gradient divided up into different zones. Someone had to spend time putting this chart together. Each zone in this chart represents a different gradient method on the preparative LC system. This is easy to run once it has been set up, but the gradient is not optimized for any particular compound. If this compound at 6 minutes or this compound at 8 minutes are the compound of interest, they will elute late in the preparative gradient. And this compound at 10.5 minutes will elute early in the preparative run. The generated gradient methods are not optimized for any particular compound. It takes a bit of time to determine the zones, and a change to either the analytical or prep system or the scouting run means a new chart needs to be made due to draw volume differences between the systems. We will discuss draw volume later. You need to set up about 5 methods for each column on the prep system. Ionizable compounds at the edges of the zone might be problematic because they may not elute when expected in a focus gradient. This is a problem common to all calculated gradients, and we will discuss this later. However, the nature of the Teledyne focus gradient generator reduces the problem because we calculate a gradient specific for a compound, so we try to make the compound elute in the middle of the run, which allows us some error in the retention time. This calculation can be used for flash reverse phase, although the chart will be different because of different gradient delays in the HPLC and flash system. The chart would work best for a single size flash column. As noted earlier, none of these compounds here need 100% solvent to elute. This is a mixture of parabens, and the green line is the gradient shifted by draw and column volume, which is the gradient delay. The second peak looks like it elutes at about 85% B solvent after correcting the gradient for draw and column volume. However, applying this focus method still causes early elution and poor resolution. An additional delay is required, and earlier work calls this several names such as the correction factor, delta, or mixing volume. This blue line is simply the time to run the sample down the prep column and can be related to the desired retention time. Teledyne ISCO explored these types of calculations and found they were not generic. A change in the system required a new correction. With this additional correction, the second peak elutes at about 65% B, which gives good retention and good resolution in a reasonable runtime. There is an easy way to determine this gradient delay. The time on target algorithm sets the retention time to a desired value with a model compound, usually 6 minutes on a 150 millimeter long column, and note that the solvent composition that causes this retention within an isocratic method. Using a matching analytical column, run a scouting gradient with the same compound using the same solvents including solvent modifiers. The retention time of the model compound in this gradient is deemed to have the same solvent composition used for the isocratic method on the preparative system. The scouting gradient is apparently delayed by a certain amount of time, the apparent gradient delay. For SFC, we set the retention time to about 3.5 minutes rather than 6 minutes. The compound to be purified is run on the same scouting gradient used for calibration. The apparent gradient delay is applied to create a focused or isocratic method, and then you simply purify the compounds. PeakTrack does the calculations on our system, and Teledyne Labs provides instructions to calibrate your analytical SFC or HPLC to your Teledyne Labs system. This is used for HPLC, SFC, and flash method development, and it actually mimics the thought process used by experienced chemists. Our first example for using method development from scouting runs and using the additional information therefrom is for natural products. Assay-directed method development uses scouting gradients to find active compounds. Unknown compounds can be found using scouting gradients by collecting fractions which are then tested for biological activity. The fractions with the biological activity are used to set the retention time to calculate the focused gradient even when no peak can be seen. The assay acts as a specific detector for a compound. This example is courtesy of the University of Illinois in Chicago. The research group was looking for antibiotics. This in theory could be done with silica thin layer chromatography (TLC) plates via bioautograms. However, other column media aren't easily available for TLCs, and reverse phase TLC plates are slow to run. The butanol extract on the previous slide was applied to a reverse phase scouting gradient on the next-gen flash system in ReadySep Gold C18 column. Butanol extracts tend to be too polar for silica and are better run with reverse phase. Fractions were collected and applied to wells in a plate. The active fractions corresponded to a UV detector peak in this particular case. The retention time allowed calculation of a focus gradient, providing a compound better than 95% pure. This example shows how running the scout gradient on the preparative system can be helpful because enough sample can be loaded for the assay. This will also work for other bioassays such as inhibition studies, which is something that cannot be done with bioautograms. Assay-directed method development combines assay-directed fractionation with method development. After only 3 steps, extraction, scouting gradient, and focus gradient, the active compound was isolated at 95% purity and identified as a diketylpiperazine. So why would I want to do a scouting run for a flash column? It's a silica column and I have silica TLC plates. Well, here are some runs from different TLC plates. All of the plates were run correctly according to the reference on this page. Yet all gave different calculated retention times. The retention time of a column in column volumes is equal to 1 over the retention factor on a TLC plate. The matched silica plates gave results that matched the column retention, but the others, particularly brand W, gave predicted retention that failed to match the elution time. Scouting runs allow sample to be run on the same silica gel column as the purification. Method development is easy for reverse phase, alumina, amine, and silica. If needed for reaction monitoring, the focus gradient generator can be used to quickly create TLC methods. The calculated focus gradient is like the solvent composition needed to elute a compound on a TLC plate. And also, a scouting run takes about the same amount of time as a TLC plate. Likewise, why would I use matching analytical and prep column? Just as for TLC plates, different reverse phase columns have different selectivity. These are different C18U HPLC columns from different manufacturers, all run with the same scouting gradient. Peak 4 was used for the calibration for all runs. The calculated focus gradients are listed for a flash column using ReadySep Gold C18. Non-matching column retention led to gradients that did not work on the flash system. Scouting runs can be used on any ISCO brand Teledyne lab system to ensure matching columns. In other words, you can run the scouting gradient on your prep system, and Teledyne ISCO also has matching analytical columns that match the C18 used for the flash columns. So what else can you do with a scouting gradient? You can determine if a compound will run well in a isocratic method. Does it need a solvent modifier? You can optimize detector parameters such as UV or ELSD settings, or for that matter, mass spectrometers. You can estimate sample loading. Can we purify a compound based on resolution from an impurity? Do we need different selectivity? Do we need improved resolution by using HPLC instead of flash? If the compounds are overlapping on your scouting gradient for a flash run, you might just need HPLC instead, or you can find a good injection solvent. The goals of the scout run are to use only a small amount of sample. Scout runs can use a much smaller sample than the prep run, as little as 0.1 mils, and I suggest that it be injected onto the column directly using the column injection port on a flash system. You can turn up the gain to 5 or 10x. In this example, use 3x gain, and that means that you use less sample. And no sample isn't lost if you use the fraction collector. You can identify the elution time for the peak of interest and identify ideal UV detection parameters. Is there a better wavelength? Does the ELSD need more gain? Many analytical systems and all current Teledyne Labs instruments can display the absorbance spectrum of a peak. This allows peak detection to be more sensitive and allow for better recovery of the desired compounds. More sensitive detection allows the fraction collector algorithm to collect the peak slightly earlier, reducing sample loss. This example, although it was detected at 254 nanometers on the scouting run, showed a stronger absorbance at 380 nanometers. This is information that you usually don't get from running a TLC plate, which only shows whether a compound absorbs at 254 nanometers. Scouting runs are typically used for calculating a gradient method, but we will show how you can optimize a detector with it. In this example, the ELSD signal is weak and is not as wide as the UV peak. This shows how sample can be lost if you just use one detector. Teledyne lab systems allow the detector gain to be increased to allow for better sample recovery. As described earlier, the detection wavelength can be optimized, and mass spectra can be evaluated to determine if the base ion peak or if the molecular ion is a better choice for detection. Scouting run data can be used to improve sample recovery. The response of any detector is sample dependent. As I described earlier, if the second peak in the compound of interest, you can increase the ELSD gain, but the ELSD is more sensitive for the first peak than the UV detector. Teledyne lab system can do collection using all of the detectors installed on an instrument, so one need not choose the best detector. Scouting runs are usually run with a small amount of sample on an analytical column. The small amount of sample usually runs without issues, but it might precipitate upon scale up to a larger on the prep system with a standard gradient. Compounds are often insoluble in the weak solvent at the beginning of such gradients. Fortunately, the calculated focus gradient reduces these issues because the gradient starts in a solvent where the compound is mostly soluble. Chemists often try to avoid solubility issues by dissolving the sample in dimethyl sulfoxide, DMSO, or dimethylfuramide, DMF. This generally works well except when the compounds elute under mostly aqueous condition. Another problem during scale-up is pH control. Trifluoroacetic acid, TFA, is commonly used for analytical systems, but is overwhelmed in preparative chromatography where the local sample concentration within a peak exceeds the concentration of the solvent modifier. An example is salicylic acid, which is in equilibrium between the polar ionized form and the free acid. The various ionized forms are depicted on this slide in the order of elution for the reverse phase column on the left side of the screen. This example is a reverse phase column, so less polar compounds elute later and the more polar compounds come out earlier. Adding formic acid to the mobile phase suppresses ionization and shifts the equilibrium to the right, as seen towards the protonated unionized form, which is less polar, as seen in the chromatograms on the right. The peak shape is greatly improved with no fronting from the early eluting material. Look for ionizable groups in your synthesized compounds because these provide a clue about whether a solvent modifier is needed. The poor peak shape in the scouting run shows that the preparative run won't work very well and needs a solvent modifier. There is no need to run a focus gradient. Instead, get good peak shape before continuing with the purification. Here's another example. Quinine is a basic compound. A scouting run with no solvent modifier showed a peak with some slight tailing. However, the calculated focus gradient showed early elution. Adding 0.1% TFA sharpened the peak in the scouting run. A new scouting run is needed because the retention time is generally different when the solvent is changed in any way. The solvent changes the selectivity. The focus gradient now gives acceptable results and the compound can be purified with this gradient. Also note that the tailing peak shape in the first scouting gradient gave a clue that the compound was not going to behave well. I wanted to know why quinine eluted later than expected with TFA, and using a pH3 buffer gave the expected retention time. This is far more buffering than most samples need, but it validated our hypothesis that compound ionization is one factor that affects calculated focused gradients. A scouting run can give clues about how much sample can be loaded on a column, on the prep column. Note that I use delta %B here rather than the retention time. Retention times in scouting runs changed based on several factors such as the flow rate or the gradient slope, but the calculated gradient start and end points will still be the same when you calculate the focus gradient. Peaks eluting closely together will have a small difference in solvent composition during a gradient, and not much can be loaded before the peaks start to merge. Peak shape affects loading. The top run used reverse phase with water and methanol. It is a successful run. The desired peak, the broad peak coming out at around 6 minutes, ran within the gradient and both compounds are resolved. Adding 0.1% TFA to both solvents improved the peak shape and the resolution. With more resolution, more sample can be loaded and the purification is more efficient. If you need to add a buffer or a modifier, run the scout gradient again because the retention will often change. For this series of runs, a small amount of sample was run that was dissolved in 1 ml DMSO. The first peak at about 2 minutes is DMSO, and the other 2 peaks are the compounds to be resolved. There is plenty of room between the peaks. Increasing the loading to 2.5 mils, that is 2.5 times the original loading, caused the peaks to merge into one another due to fronting from the DMSO. As the mobile phase is mostly aqueous, the sample can be dissolved in water, the weak solvent. This allows the compounds to be concentrated at the top of the column. 2.5 mils of a water injection at the same concentration as the DMSO samples gave excellent resolution with high loading. DMSO and DMF are often a stronger solvent than the mobile phase, causing poor peak shape in high loading situations. The sample can generally dissolve in water if the calculated gradient shows elution is less than 30% organic solvent. Samples sometimes have late eluting impurities. The sample can then be dissolved in a minimum of DMSO and then diluted with water. The sample should then be filtered prior to injection to remove the nonpolar impurity that might precipitate. Some labs need everything dissolved in DMSO, and in these cases use as little DMSO as possible to avoid changing the peak shape. Scouting gradients are useful to calculate focus gradients for peptides. Buffering is important for peptides, and sometimes a column screen is useful. The scouting gradient gives a quick look about the compound purity. This peptide has several impurities that elute later, which will cause long cycle times for a stacked injection. This peptide can be pre-purified on a gradient run on a flash system or HPLC. Because the major impurities are greatly resolved from the peptide, the column can be heavily loaded to reduce the number of injections needed. This peptide shows several multiply charged ions on the mass spectrometer, making identification easy. However, there is a shoulder ahead of the main peak. The different mass spectrometer traces show it is the same compound. This shoulder suggests that the compound should be run at a different pH or buffered. Cyclic peptides will sometimes show multiple peaks for the same pure compounds due to multiple stable conformers that can be resolved. In this example, the peptide was fairly clean but has closely eluting impurities visible on the UV trace. The peptide was focused to an isocratic run and then was run as a stacked injection. We shaved off the impurity with the time windows. As the purification was well characterized, the mass spectrometer was not used, thus keeping that instrument clean. This is an example of a column screen. This is a natural product isolated from cumin root and purified with a flash C18 column as a single peak. A column screen was run and the compound looked like it was pure until the PEI column was run on the SFC system. This showed 3 peaks and each was a different compound as per the mass spectrum. The scouting runs show which column was best for the final purification of these compounds, and an isocratic method was calculated from the scouting run for the first eluting major compound, and the solvents can be screened as well. Do you have any questions?
Well, thank you, Jack, for sharing this informative webinar with us. It looks like we have received a few questions. So with that, I'll turn it over you to answer.
Thank you, Sharon. Our first question is about SFC. Why is a different retention time for the focus gradients used for SFC? And it's just because SFC runs much faster, so a shorter time is used. The next question is, why don't we set the gain high for all of the detectors all of the time? The reason for this is if the peaks saturate the detectors with the gain set so high, cutting out impurities is much more difficult. We have another SFC question. My SFC only goes to 50% co-solvent. Can I use it for scouting gradients? Yes, although the results will be limited to 50%. You can try the scout run on the AccuPrep SFC, which goes to 70%. This question is, I have several analytical columns and prep columns of different types. Do I need to do a calibration for each type of column on my prep system? No, provided the analytical columns are all the same size and use the same scouting gradient method used for the calibration, and it will work. Another question is, do I need to do new calibrations for different solvents on my analytical systems? No, as long as the scouting run is the same calibration works for all solvents.
Well, thank you, Jack, for sharing your expertise. If any of your questions were not answered, please know Jack will be responding via email. This webinar has been recorded, and we will be making the webinar available to you in the near future. So with that, I would like to wish you all a beautiful day, and I hope you can join us again next time. Take care.